Hi, I'm Professor Orr, your animated guide to all things chemistry. In this video, I will try to make sure that you will never make any mistakes writing organic structures again by showing you the number of bonds and lone pairs of the typical elements in organic chemistry. So let's get right to it. If you've taken an introductory course in chemistry, you probably had questions like these. Write the Lewis structure of CH4, for example. To solve this, you would have to first write the individual atoms with their valence electrons drawn as dots, like so. This is a valence electron, which are the outermost electrons most likely involved in bonding. And then you have to pair the electrons between the atoms so that each atom has a full electron shell, which is the most stable form for an atom. And you can then write these shared electrons as lines, which are essentially chemical bonds. Now, in this Lewis structure here, both hydrogen and carbon have a full shell. For hydrogen, this means 2 electrons. And note that we count both electrons in the bonds as electrons belonging to hydrogen. The reason for this is that the hydrogen atom has only 1 electron, which therefore occupies the lowest energy level, which corresponds to the 1s orbital. And because the 1s orbital can only have 2 electrons of opposite spin, a full shell for hydrogen indicates only 2 electrons. Now for carbon, the situation is a bit different. In this case, a full shell indicates that it has 2, 4, 6, 8 electrons surrounding it. This is because carbon has more electrons than hydrogen. It has 6 electrons. This means that they do not only occupy the lowest energy level, the 1s orbital, but also the second lowest energy level. And this level has both the 2s orbital and the 3 2p orbitals in it. As each of these can accommodate 2 electron pairs, a full outer shell indicates 8 valence electrons for carbon. Now this is pretty common for many other elements as well, but not all, and it is called the octet rule, which states that atoms will gain, lose, or share electrons to achieve a stable electron configuration with 8 electrons in their valence shell. Now let's try another example to see how general the octet rule is, and let's write the Lewis structure of C2H4. We do the same thing. We first write all atoms with their valence electrons, pair the electrons, and then write the paired electrons as bonds. Now if we just stop here, each carbon still has an unpaired electron and does not have a full octet. So what we can do is to move these electrons closer to each other so that they can actually pair and form a bond. And in this case, we formed a double bond. Now, with a double bond, we count them as 2 single bonds, and they therefore contribute 4 electrons in total to the valence shell of carbon. And combined with the other 2 bonds to hydrogen, which each provide another 2 electrons, we have 6, 8 in total electrons around carbon, or a full octet. Now let's take this one step further. Let's try to write the Lewis structure of C2H2 now. Once again, we write the atoms with their valence electrons, pair them, and turn them into bonds. We now have 2 unpaired electrons left per carbon and still no octet. So we rearrange the electrons again, and now we form a triple bond between the carbon atoms. And once again, carbon has a full octet in this structure. So the octet rule is pretty general for carbon. But it's not only carbon that we're interested in. Let's take an example with nitrogen, like NH3. We once again start with writing each atom with its valence electrons, which is 5 for nitrogen and 1 for hydrogen. And when we now pair the electrons of nitrogen and hydrogen to form bonds, you'll see that we are left with 2 electrons on nitrogen. Now because orbitals can accommodate 2 electrons, and nitrogen already has an octet in this configuration, don't have to do anything special with these electrons, and they remain there as what are called lone pairs. And so basically, to write Lewis structures, you first need to know the number of valence electrons of the atoms, and that automatically tells you the number of bonds and lone pairs this atom can have. Now this might seem a little bit daunting as it requires you to know the number of valence electrons for each element in the periodic table. Now luckily, for organic chemistry, only a handful of elements are really important. We don't need the noble gases as they don't react with anything. We also don't use the lanthanides and actinides in organic chemistry, nor the transitional metals all that much. And we're just focusing on what are called the main block elements, which can be split into the S block elements in red and orange, and the P block elements in green. They are named that way because their valence electrons are located in either an s orbital or a p orbital. Now, the nice thing about the main block elements is that you can number them from left to right with their group number, and these group numbers then nicely correspond to the number of valence electrons. And so it's quite easy to know the number of valence electrons for these elements. Now, in addition, we are really only interested in the first and second row elements, which all follow the octet rule. And so this means that the number of bonds and lone pairs for these atoms can be easily predicted. So let's start with the S block elements. We leave out hydrogen for now, as it is a category on its own. But the S block elements are really not that common in organic chemistry. They are all metals and are either found in their neutral, metallic state, where they don't form bonds to anything, or as cations in salts, think of lithium plus, sodium plus, or potassium plus for the alkali metals, or beryllium 2 plus, magnesium 2 plus, calcium 2 plus for the alkaline earth metals. But as I said, they're not the most important elements. Let's look into more detail at the P block elements, which are much more important for organic chemistry. So we will start with the first element in the P block, boron. Boron is in group 3 and thus has 3 valence electrons. This means that it can form 3 bonds with no lone pairs. Now, you'll notice this is not a full octet, but it is the only thing possible for boron without building up charges. The next element in the P block is the most important element in organic chemistry, carbon. Carbon is in group 4 and thus has 4 valence electrons, which are then capable of forming 4 bonds with no lone pairs. And this is probably one of the most important rules in organic chemistry that you should always look out for. Carbon normally has 4 bonds, and it will never have 5 bonds or even more than 5 bonds. If you write the structure with 5 bonds on any kind of exam, you will probably lose a lot of marks. So, moving on to our next element, nitrogen. Nitrogen is located in group 5, so it has 5 valence electrons. Now, if we would use all valence electrons to form bonds, we would have 10 electrons and thus exceed the octet rule. So therefore, nitrogen will normally keep 1 lone pair and form only 3 bonds to satisfy the octet rule. Next up is oxygen, which is in group 6 and thus have 6 valence electrons. Similarly to nitrogen, in order to obey the octet rule, oxygen can only have 2 bonds with 2 lone pairs. The next P block element is fluorine, but we will extend this here to all the halogens. Fluorine, chlorine, bromine, and iodine, as they all behave similar and they are all equally common in organic chemistry. The halogens are in group 7 and thus have 7 valence electrons. This means they only need 1 extra electron for a full octet and thus generally form only 1 bond and then have 3 lone pairs left. Now finally, we will also cover hydrogen. Now hydrogen is technically not a P block element because it doesn't have a p orbital, but it has a lot in common with the halogens. So hydrogen has 1 valence electron, but it only has a 1s orbital and therefore it only needs 1 extra electron for a full shell. And so hydrogen therefore only forms 1 bond, just like the halogens, but it has no lone pairs. Now this list that you see here is very important if you are learning organic chemistry. Now you can derive it from first principles like I just did, but most people find it easier to just memorize these numbers. The only thing that you should note, however, is that these numbers only apply for neutral elements. When elements have formal charges, their number of valence electron changes, and so do the number of bonds they form. So, for example, when elements have positive charges, they have fewer valence electrons than normal, and so the numbers will change. So if we start again from left to right in the periodic table, we should start with boron. However, boron is a bit of an exception, as it couldn't even form a full octet when it's neutral, so let alone if we take an electron out, cannot really ever get to a full octet, and so positively charged boron is very rare. The most viable option is to remove all of the valence electrons and be left with boron 3+, which in this case has a full 1s orbital and so a full closed shell. This is basically a cation with no covalent bonds and no lone pairs. So more interesting is carbon. So normally carbon is in group 4 and has 4 valence electrons, but a positive charge means that it has 3 valence electrons. Now this also means that it can only form 3 bonds, and therefore it does not have a full octet. As a result, such positively charged carbons, which are called carbocations, are generally unstable and very reactive, but very important in organic chemistry. Next, for nitrogen in group 5, to have a positive charge, it only has 4 valence electrons. And so to have a full octet, these 4 electrons will form 4 bonds and there are no lone pairs left. Similarly for oxygen, it normally has 6 valence electrons, and therefore to have a positive charge, it loses an electron and has only 5 valence electrons. This way, to form a full octet, positively charged oxygen will form 3 bonds and keep 1 lone pair. For the halogens, a positive charge implies only 6 valence electrons instead of the usual 7, and so they will need 2 bonds to form an octet and are left with 2 lone pairs. Now hydrogen, it's a bit of a weird one because it only has 1 valence electron. So therefore, if it has a positive charge, it basically has no electrons left and it is just a proton. So many chemists therefore refer to H+ as a proton. And a proton has essentially 0 bonds and 0 lone pairs, but it is very common and important in organic chemistry. So that's it for our common positively charged elements. We can do the same thing to figure out the number of bonds and lone pairs when these elements are negatively charged. Now here it is important to remember that a negative charge implies that there will be more valence electrons than normal. So if we apply this to boron, which is in group 3, we are expecting 4 valence electrons for negatively charged boron. And thus, when negatively charged, boron has 4 bonds, and this is the only time that boron has a full octet. And as a result, negatively charged boron is relatively common. Now for carbon, which normally has 4 electrons, a negative charge implies a total of 5 valence electrons. This allows carbons to form 3 bonds and keep 1 lone pair. And these negatively charged carbons are called carbanions. Next up is nitrogen, which is in group 5. So for a negative charge, we expect 6 valence electrons. Now this allows negatively charged nitrogen to form 2 bonds and keep 2 lone pairs for a full octet. For oxygen, a negative charge suggests 7 valence electrons, and so oxygen only needs 1 bond to achieve a full octet when negatively charged. Oxygen then remains with 3 lone pairs. Now for our halogens, something interesting happens. Because they are in group 7, they normally have 7 valence electrons. But when they are negatively charged, they have 8 valence electrons and are therefore already a full octet. And so negatively charged halogens are perfectly stable anions called halides. They do not form covalent bonds and just have 4 lone pairs around them. Hydrogen, very similar. So when negatively charged, hydrogen has 2 electrons and therefore a fully filled 1s orbital. It therefore does not form any bonds and just has a single lone pair. And negatively charged hydrogen is called a hydride, similar to the halides for the halogens. Now this final table is probably one of the most important guidelines for writing structures correctly in organic chemistry. As I mentioned, you can derive it from first principles, principles, but most people do find it easier to just memorize the table. Now, this can be hard and frustrating for some, but to make it a little bit easier, you can download a PDF version of this table on professororgo.com to help you with your studying. Now, before I end this video, let's bring back all the main group elements. So far, I've only covered the first two rows of elements, because these are the most important elements in organic chemistry. However, some of the third row elements also occur in organic chemistry, and sometimes even the fourth and fifth row elements as well. So let's have a closer look at the elements in the third row. If you've taken a general chemistry course, you should probably know that elements in the same column of the periodic table generally behave similarly. And so sodium, like any alkali metal, is either metallic or sodium plus. Magnesium, like any alkaline earth, is either metallic or magnesium 2 plus. Aluminum, in group 3, behaves a lot like boron and has a default of 3 bonds, while silicon in group 4 behaves a lot like carbon and has a default of 4 bonds. Now the problem arises with some of the later columns. This is because the third row elements have more electrons. Therefore, the first energy level and the second energy level are completely filled, and the valence electrons are located in the third energy level. Now, this energy level houses the 3s orbital, the 3p orbitals, and the 3d orbitals. Now, while the 3d orbitals are normally not filled in the main block elements, the fact that the third energy level has 3d orbitals means that these elements can accommodate more electrons than normal, and therefore they can exceed the octet rule. For example, phosphorus is in group 5, and so it has 5 valence electrons. And same as nitrogen, this means that phosphorus can form 3 bonds with 1 lone pair in order to have a full octet. However, because of these 3d orbitals, phosphorus can exceed the octet rule. This means that it can also use all of its valence electrons to form 5 bonds and have no lone pairs left. This is actually very common. The most common form of phosphorus in organic chemistry is probably phosphates, which have 5 bonds, 3 single bonds and 1 double bond. A similar situation occurs with sulfur, which is in group 6 and thus has 6 valence electrons. Like oxygen, which is also in group 6, it can form 2 bonds and keep 2 lone pairs to achieve a full octet. However, similar to phosphorus, sulfur, as a third row element, can exceed the octet rule due to its 3d orbitals. And this could imply either 4 bonds with 1 lone pair or using all its valence electrons in 6 bonds with no lone pairs. The final third row element is chlorine. This is a halogen, and I already mentioned them before. Most halogens just form a single bond with 3 lone pairs. Now, the higher halogens, chlorine, bromine, iodine, they can break the octet rule, and in theory can form 3 bonds with 2 lone pairs, 5 bonds with 1 lone pair, or even 7 bonds with no lone pairs. This is, however, pretty rare in organic chemistry and is only common for iodine. In general, for the halogens, you should just assume that they only form 1 bond. With this, I have explained the number of bonds and lone pairs for the most common elements that you will encounter in organic chemistry. And as I mentioned, you can derive them, but most organic chemists just memorize them. In fact, these numbers are so natural to organic chemists that we usually don't even write the lone pairs when we write structures. Instead, when we see a structure like this one here, we just automatically know where the lone pairs are and how many there are. And furthermore, we also don't even write hydrogen atoms on carbon in most structures. We just know that we have to add hydrogen atoms to the molecules to make sure that each carbon has 4 bonds, unless if there's a charge on the carbon atoms. And so hopefully, after watching this video, you will have the same skill of immediately recognizing how many lone pairs there should be on each atom and how many bonds each atom should have. If you enjoyed this video, please like and subscribe to the channel. and let me know in the comments which other topics you would like me to cover. I'll see you in the next video. Bye.